All right, good afternoon, everyone. Welcome to our next in the series of our RQC seminar series. Today, we will be joined by Dr. Eugene Dumitrescu from Oak Ridge National Laboratory, where he will be discussing a holistic software stack for domain science applications. And I believe much of this work is being conducted under the DOE QCAT stack project. Eugene, welcome and thank you for joining. Before you start, and I'll ask you to share your slides just in a moment. I also wanted to highlight next month's meeting. And I can't go to the next slide. Here we go. Next month, Dr. Bert de Jong from Berkeley Lab will be speaking about their projects, AID-QC as well as others. So stay tuned for that. And of course, we'll be having announcements on that one as well. So without further ado, let's go over to Eugene. I will stop sharing, and Eugene, please go ahead and share your slides. And thank you for joining us.
So thanks, Dave, for really setting up this entire series and having me talk early on. So I will be talking about our QCOR project, and I kind of wanted to just start by telling you guys that there's a website where all the information that I discussed today is discussed in more detail. So things like research thrusts, all of the people, you can find nice links for them, get their email addresses, and list of publications are here. Okay, so I hope the presentation, you can see that?
Yes.
Okay, great. So first of all, yes, we have to thank DOE funding for this wonderful project that we have. I'm representing the software stack for and algorithms for automating quantum classical computing, STAQC. So here are our, let's see if I can do the old laser pointer. Okay, great. Here's my information if you need to contact me. I would also say some of the people in this on this team are here, so if you have questions, probably the chat is a good place to put them, and they may actually be able to answer them in the case that I don't know the answer. So these are our partner institutions, and I guess I would start with a little bit of motivation for our project, which if you came to Fred's talk last month, he showed lots of really cool research results in compiling and formulating more efficient schemes for measurements and et cetera, et cetera. And he made some comment like, wouldn't it be great, you know, we need a integrated software stack to really implement all these things. And that's basically what our feeling was as well. And that's why we proposed this project. And so we have kind of 4 layers. And the point is that even if you're a domain scientist, it can be quite difficult to compile your problem all the way down to the hardware level really efficiently. So we're attacking this quantum computing kind of in a scale invariant way, looking at both the big picture and lots of little finer grained details, and trying to compose them all together in a way which is self-consistent. Okay, so I'll just kind of go through the stack really quickly before jumping into the details. So what we mean by domain science is things like this. So we have this group of people, some of which you may recognize, who actually do real domain science. And whether that be perhaps some machine learning task, we also focus on condensed matter, on high energy physics, and a little bit on algorithms in general. You know, these are the kinds of things that they're thinking about at the high level. And now if you go down one level, we have a programming language. And I'll get into all the details of what all this stuff means, but the point is that we've constructed a language extension that's supposed to make it simple for the domain scientists to express their problem of interest and perhaps some methodologies and algorithms in a way which is amenable to quantum computing. And then when we go down one more layer, that's great. We have a language, but you then have to run through the compilers, the thing that then, so I'm kind of combining domain scientist here with the programming language. And now we say, we have to compile that if it's a nice expressive language down to something that can actually run on a hardware. So in the compiler, we're focusing on these three areas right here, which I will get into later on. And then down at the hardware level, we're still in a NISQ era, so it makes sense to squeeze out as much performance from the hardware and really think about, what are the kind of interesting things that we can do, whether it be mapping problems directly onto hardware in kind of an analog manner or quasi-analog, whether it be considering noise characterization, noise control, things, kind of anything like that, or quantifying error, doing error mitigation, et cetera, et cetera. Okay, so let's go all the way back to the top, and I will now present for the next while quite a few results from the domain science thrust. And I guess if somebody has any questions, please speak up, maybe via Dave. I'm ignorant if any chatter is, if any questions exist.
Yeah, sorry, Eugene, I'll jump in here. I forgot to mention at the start, the way I think that works easiest with these large Zoom calls is if you have a question, throw it in the chat and I will be monitoring while also trying to make sure my kids are okay over on the side. But I'll be monitoring the chat and I'll jump in and ask the questions along the way.
Okay, thank you. Yes. All right, so to begin, I'll talk, one of the thrusts on the domain science side is applying quantum computing to high energy physics. And as you can imagine, this is kind of a incredibly complicated, or can be incredibly complicated to formulate these problems onto a quantum computer. I don't think it's been, it certainly hasn't really been fully accomplished yet. So the team is mainly our collaborators from UMD, University of Maryland, Zora and Drakshi, Andrew Shaw, and others that I will highlight soon. And they're focusing on putting lattice gauge theories on a quantum computer. So a lattice, I think everybody knows what a lattice is, but a gauge theory is a special kind of theory where a field theory of a particular, which has a particular set of constraints such that under certain transformations, the theory remains invariant. So kind of the basic gauges, and gauge actually I kind of learned about it while reading here. Really refers to a measurement, and the idea is that really measurements are actual physical measurements are invariant under transformation. So gauge theories, if I may call them that. So things like I have a ball on a hill or in a well, and it doesn't matter the dynamics of that ball do not transform under me pushing this hill up or down with respect to a zero reference, or alternatively the electromagnetic potential is gauge invariant under certain transformations. Okay, so here the theories that are being studied kind of contain a couple components, and really the work right now is going into just even formulating the problem and putting it on the quantum computer. Okay, so we won't even really get into too much into proper dynamics algorithms or other things. So I'll just kind of illustrate what is actually happening here. So we have a, so let's begin here. These psi's refer to operators destroying and creating fermionic particles. And we can have particles and antiparticles, as one does in high energy. Then we'll also have some gauge some gauge boson field. So this could be like my electric field, or it could be my color field. And in two-dimensional formulations, magnetism will appear, and they're coupled through this kind of this form, where now the fermionic variables, when they hop from one site to the next, they'll interact with this gauge variable defined on the link. So I should be showing you guys that the fermions will sit on these sites. There will be these electric field operators on the left and right of the link operator, and there's a gauge degree of freedom which sits on the link. Okay, so it's kind of a complicated theory already, and what happens is that there will be some set of constraints, these gauge constraints, which ensure physicality of your configuration. So you can imagine things like Gauss's law. So if I have a charged particle, I need to have the right amount of electric field diverging from my source. And if I just kind of naively put my, encode all of these variables into qubits, then the entire Hilbert space has many kind of very strange configurations with electric field scattered around and particles not emanating electric field and so on. So really, there's a very small sector of the Hilbert space which actually is gauge invariant and satisfies these generalizations of Gauss law. So it's in fact quite difficult to even formulate a nice encoding of these problems due to the fact that all of the gauge constraints do not commute with one another, and so on. Okay, so our colleagues here have done quite a thorough beginning investigation of different kinds of formulations of field theories, of non-abelian lattice gauge theories, I should say. And they consider a variety of different encodings where so by fermionic, purely fermionic or purely bosonic, in certain cases, one is able to integrate out either the fermions or either the bosons. There are some pros and cons for each of them. So they can be efficient, but for example, they might only be valid for open boundary condition configurations. You can also reformulate it in terms of a angular momentum basis. I guess there's some problems in going to more general SU3 theories, which of course we'll want to go to for QCD. And what we'll discuss, what I will highlight here is this LHS formalism, in which Gauss law constraints are imposed by construction. And there seem to be quite a few pros in terms of going to higher dimensions, going to more complicated gauge, non-abelian gauge fields, etc. And they in this, if you look up this paper, you'll see that they do a asymptotic scaling analysis for qubits needed, gates needed to perform certain operations, and LHS seems to be it's very competitive in its scaling, and it has some very nice properties. So that's a nice takeaway here. So I'll say a little bit about it, although again I'm not a complete expert in this. So this has really been spearheaded by Dumitrescu, in these first two papers, and then this third paper is actually a cold atomic simulator proposal to realize such theories. So here the idea is that we're going to completely re-encode the theory in a different basis, and in terms of and this basis will be a local basis, and in this way we'll be able to construct instead of using these complicated Gauss law constraints which don't commute, etc. You construct the theory out of in kind of a different way with these. So sorry, I should say LHS stands for loop hadron string formulation. So you kind of think about the elementary Legos of your model to be these strings and then these hadrons, and they obey some kind of very simple constraints which just involve number operators. So you can in fact build a gauge invariant state just by, say, starting on one side and following these occupation number constraints as you go along in your theory. Okay, so that's kind of a nice point, is that the abelian constraints are mapped to simple occupation number constraints. It's also, like I said before, generalizable to 2D and 3D. That's what this is indicating. And in some sense, there's not a very big difference in going from 1D to 2D to 3D. And Dumitrescu and collaborators have also come up with things like, so let's suppose I encode this on a quantum computer now, the way that's drawn up here, and I wish to actually check, am I in a gauge invariant state? Is my state a gauge invariant? Then I have to consider check these constraints, and they've done all the circuit analysis. And this is actually, I know it's a small picture, but it's for a two-dimensional system. And even when you go to a three-dimensional system, kind of all of the fundamental components don't change. So it generalizes very well. Okay, Zora and collaborators have also worked on simulating lattice gauge theories with trapped ions. I won't explain this in any depth, but I'll just say that basically they've thought about how can I map the effective ion Hamiltonian to the Hamiltonian of particular lattice theories. And so you can, I guess it's kind of been known that you can do this. You can do the Schrodinger model. I believe here they have integrated out the gauge field. So this leads to a long-range spin interaction model. That's right, and this is just okay. They've also looked at things like Chern-Simons theories in 2+1D and Z2 gauge theories in 2+1D. So lots of field theories. Back. I guess I put these out of order, but this is the reference for Dumitrescu's cold atom simulator, and I think I'm not able to explain it in any detail, so I will leave it here for you to check out this archive listing. Okay, so now I will slowly transition over to condensed matter by highlighting an application that's come from Brian Swingle on our team, Brian Swingle and collaborators, which is at the intersection of high energy physics and condensed matter. So basically what they did is they defined and studied a sparse SYK model, which is kind of, you can think about it as a path to simulate some types of quantum gravity on a quantum computer. So the basic idea is builds upon this duality, ADS-CFT duality. And so it turns out that this model drawn right here, where these chi's are Majorana fermion operators, which are coupled kind of in a random fashion, they realize if you put them on a ring, you get something that looks like a gravitational theory on the dual of this holographic duality. And so that's fine. It's a nice toy example. But what they did is they showed that what I can do is I can take I can think about this this JABCD as a kind of a coupling matrix between all the Majoranas. So they live on a graph where they could all talk to one another, and they'll put this x variable, which is equal to either 0 or 1 with some probability. Okay, and there are some property. You know, this model has to. So these guys are Gaussian variables, and this choosing some of them to be 0 on or off renormalizes the variance, but nevertheless, they're able to kind of interpolate between different limits of this model. And what they show is that basically in certain limits they can sparsify the model and still maintain the physics of this quantum gravity on the dual side. And so this has basically led to kind of a twofold developments in that you know, we're able to study these kinds of processes in duality classically because this model is further sparse than previously accessible, and it's improved basically the best quantum algorithms to study quantum gravity. And so I give you some scaling here that you can find in their paper, and I believe this relies on some type of qubitization. Okay, so kind of slowly diving deeper into condensed matter applications, Christopher White and collaborators have also worked on quantifying the complexity of condensed matter theories in terms of magic, which is you know, what you'd like to know in the fault tolerance setting, and I guess magic is kind of well, okay, I'll get to the punchline later on, but yes, magic gates are T gates are expensive in terms of fault tolerant quantum error correcting code implementations. So that's why that's the metric of interest. And they will study this 1D Z3 POTS model, where that as a theory of I don't know exactly why I don't remember why they studied this model, but I guess it kind of has, it does show some interesting properties. And so what they basically do is so here's, I've written the theory, well, I've taken slides from Christopher, where he's parameterized the theory in terms of an angle theta. So theta, if you tune theta from one side to the other, you'll go from one phase into the other phase. And so basically what I'm showing you here is that they've done some subsystem calculations to quantify, actually it's this thing called this mana density, which is related to the amount of magic needed to construct the state. And you see that at the takeaway here is that maybe unsurprisingly, these theories, these states are basically quite hard to write, or sorry, they're mana density slash magic resource requirements are quite large at this phase transition between the small theta and the large, this kind of pi by 2 limit. And the interesting thing is that what their calculation is, I'm probably not describing it well, but the takeaway here is that so magic can also kind of be a local quantity that doesn't really do anything interesting for you. So I could take like a product state and rotate all spins by some very small or some kind of random angles, some random phases, and that will be like some super high, or that will be some state which requires a large number of T-gates to realize. But they've shown that that this magic is large and it's non-local. So this is kind of like genuinely necessary and difficult. This magic is really needed to encode these states, and it's not just kind of some trivially unentangled thing. And they've also studied the thermal states as well. Lastly, on the condensed matter side, Jim Freerichs and collaborators have been looking at Hubbard model and looking at the complexity of even doing a state preparation. And so this is kind of motivated by, so this is a factorization of the ground state which can be generated by some product formula, and that product formula is a factorized form of the unitary coupled cluster ansatz. And this is an exact parameterization for a four-side chain described in momentum space. And if you look at their paper, you will see kind of exactly what are the angles needed to exactly factorize this thing. And the interesting thing is that you basically need a quad excitation in order to generate this. So they're really looking at the kind of quantum density to prepare correlated electronic matter, and they've looked at how this parameterization changes as you tune the interaction energy. And there are some kind of ongoing efforts that aim to use this information for smart algorithms, which is kind of in the works, so I won't say more about it. But and then another kind of interesting thing they've looked at, and there's more in the paper, is so here they've used actually an approximation, which is a coupled cluster factorized ansatz using only doubles, so without this quad thing. And they've looked at what is the approximation error as a function of U, but I think this is kind of a pertinent question in much of electronic structure theory. How much correlations do you really need, and how much can you get away with ignoring in some sense to still get an answer, reliable answers within some epsilon. Okay, so moving on to kind of hardcore algorithms, Itai Hen has done some very nice work kind of rethinking how quantum simulation or can be formulated. And so the basic idea, actually, I do recommend this paper. It's very nicely written. So they use the following kind of mathematical fact. So any matrix can actually be written as a summation of a bunch of permutation matrices. So you okay, so here's a matrix and here's a bunch of blocks, and here they are written in some basis, and I think you can kind of see that this one is something like x1, this one is something like x2, and this one is x1 times x2, if I'm calling x the Pauli matrices. And of course, what that's really, you can rethink that and say, oh, well, that's really some diagonal thing times a different permutation matrix. So this first one is diagonal, duh. And then the second one is some diagonal times a permutation, and so on and so forth. And if you are careful in your expansion and kind of counting and reordering, then you can realize that you can write this something like a real or imaginary time propagator as a sum of different possible products of. So it's an expansion in terms of these products of permutation matrices. And then if you can kind of, Itai is smart about the way that he evaluates these guys in a computational basis and transitioning between computational bases. And they can group together all terms which have the same quote unquote off diagonal core. I mean, all terms, not just terms up to some particular, n in your Taylor series. I mean, all terms. So you can find this core and evaluate all things, all of its contributions. So it's kind of like a alternative to a Taylor series in some sense. And if you you can think about quantum simulation with this thing, and he's done some scaling analysis of LCU simulation using this technique instead of Taylor series LCU. It's like off diagonal series expansion LCU, and here the kind of nifty thing is that you can you factorize you factorize through all of the diagonal evolution into one block here. So it's you wouldn't have to, so if we have some of these models, you'd need a term for each of these in conventional LCU, but they're grouping them all into one term, so there's some reduction in the complexity. Kathleen Hamilton has been researching the actual use of near-term devices for machine learning. So there are actually, I believe, she has quite a few more papers than is just indicated in this highlight slide that she has sent me. But this is a slide showing that, showing to the extent at which quantum devices can be used to do nonlinear series forecasting. So there's some time series data, and given components of that data, you want to train the machine to tell you what's the next step of your time series. So I recommend you check out this this paper if you're interested in this. And these are real. These are simulations and actual hardware results. So a lot of times theory can get very far ahead of hardware, and so she's actually studying what hardware can actually do. Okay, so that's a ton of applications, and I've used up most of my time already, so I'll kind of have to speed up. But okay, so we have all these really cool applications, but you kind of like, you want to express them, and then you want to really get them down to the hardware. So you have to go, so that's the goal of us, that's the goal that we had in creating this programming language extension. So our team is here. Chung Sing is our new thrust lead. Chung Sing, if you're here, I'm sorry. This is a picture I found of you on one of your websites. So the idea is basically we want a programming language in which you can actually really express domain science problems. Then to begin, we're thinking about quantum classical, say iterative or variational approaches. We want to really part of the goal of this project, and the point of it was to adopt good practices, best practices from HPC and computer science community. It's also pretty cool that you can, it's also a kind of single source approach. So like single source meaning, I can just sit there in C++ and I can write down something native C++. This language extension allows me to write something, kind of modify C++ to understand what, for example, a quantum circuit is, and run a quantum classical program. So our focus areas were in defining an execution model and a memory model. They're basically, this is a little bit of a dated publication from a year or two ago, and but I think it kind of gives you a good idea of what our model is, modulo small modifications. So we think about a host device with and a quantum device consisting of a QPU and some memory maybe at the controller level, and then there's some shared memory, and we are writing this C++ extended code, compiling and running through a variational loop with memory management routines. And we have a bunch of data types and APIs which are useful for basically encoding domain science problems, running this variational model of hybrid quantum classical computation. They're generic enough so that they can be compatible with non-variational and fault-tolerant methods, but we kind of haven't really done too much actual work there. So this would be a great place to collaborate with us, perhaps. And there's lots of great functionality in there. So let me show you just a little some of the data types and APIs. So we have things like, one of the main data types is an operator, right? You can express all those things in the condensed matter, HEP, even machine learning. If you think about it in terms of operators, they're going to allow us to to verify algebraic properties, etc. Okay, so this is important, and then we have lots of other data types and APIs to say allocate memory on the quantum device and the classical device. Where do you keep the memory? How do you handle it? Also, we've kind of packed up everything neatly into this thing, into a task, which consists of an objective function, which has a cost function, some parameters, and a circuit. And now you can optimize this objective function with the use of some, you can pick whatever optimizer you can find, and some extra little properties to help everything actually get compiled. So I'm going to kind of speed up a little bit, but here are some APIs for operators and some algebraic routines. Okay, so now let's kind of go through the compiler. So the compiler is this thing that combines this QCOR source code, does some syntax handling, and uses the pre-existing libraries that were also developed at ORNL, and it can do a lot of things, and send to a variety of devices. It can translate between languages. There are, through the use of an intermediate representation, we can run optimizations and transformations. So here I'm just going to basically showing you that we have a working implementation that has the components from the previous programming language section. So we have a quantum kernel that's written natively in C++. We have constructs, operator constructs. We have the objective function. You can call whatever optimizer you want. So here I'm kind of showing you all the different pieces, again, in a bigger view so that you can really see them. So, some kernel means circuit in my mind, but it's a circuit that you're going to offload to QPU. Allocate memory, objective function. So task initiate is this thing that's going to kick off an asynchronous job optimizing your objective function. So you can go off and do something else, or maybe you can kind of just stream in data asynchronously and optimize. And at the end of the day, you're going to synchronize, get back your results, at the end. Okay, so here are a bunch of
Eugene.
Yes.
Quick question from Will Zhang. He asked if QCOR has or today or any plans for quantum arithmetic libraries.
Yeah, I think that's the that's part of that kind of fault tolerant model that we want to expand into, and not yet, but we would love to add that. So you can check all of this stuff out. It's all open source. Here's a bunch of papers, and really the person to talk to about any details is going to be Alex McCaskey. And there are lots of examples there of all sorts of things. And we're very happy to collaborate, yes. Okay, so finally, in the last 15 minutes, I would like to just touch on this last component. So, we've had our problem, we've expressed it, we've compiled it, but really there's a whole lot to be said for actually the hardware layer as well. Whether that be error mitigation, whether that be some kind of quantum control, or anything else, there's really, for now, there's a lot that has to be done, and we kind of hope that developments here make an impact in long-term quantum computing. So I will first tell you about, finally we get to some of my work. So we basically thought that, well, we have all these cool devices, but it's hard to do something, we have depth restrictions, et cetera, due to noise, due to correlations, whatever. And we were kind of inspired by some native use of Hamiltonians. And, but even if you want to do that on, say, IBM, you can read the paper, but that doesn't tell you what their Hamiltonian actually is. So the question is, what is the Hamiltonian of a quantum system, and namely one that is open to the environment? And there are, previous methods, process tomography, Bayesian learning, which kind of are difficult and unwieldy in their complexity. And then there's a class of scalable methods, which utilize locality. So, so that's what I'll be talking about. So the picture here is like, as a mathematical operator, a Hamiltonian has an exponential number of terms, but so I could try to infer them. But if it's exponential, then there's no way I can take enough data to learn that. However, if I use locality, so by locality I mean I will restrict my Hamiltonian to some basis where the basis elements are just polys which are inside of some box of some size. Now I actually have something like something that's growing linearly in my with my volume, and constantly in my locality. So one has the hope to actually learn such a thing. And so the basic idea here is we generalized some previous work and showed that if there's kind of another setting that I'm not going to have time to talk about here, but if I can make something that's a stationary state of a, say, Lindbladian, right? So my state doesn't evolve in time, then I can think about going to a Heisenberg picture, a Heisenberg-Langevin equation, where I look at the time dynamics of a bunch of operators. I can think about any operator, and the time dynamics is 0. So what I can do is I can actually measure a bunch of correlation matrices for different O's. I can, as many as are needed in order to obtain enough information to determine my model, given a locality. And I build up these correlation matrices, which so A is like a matrix of a bunch of is this thing with a bunch of different O's, and B is the Lindbladian version, and I'm going to consider some model parameters in my C and gamma vectors, and this becomes a linear homogeneous equation. And basically, what I can do is I can take a bunch of data, look for a 0th eigenvalue, find this, use that solution, and that's my estimator. So this really quickly is just the kind of test model that we use. So it's I just put some random, well, not completely random, but just some values on polymatrices, some couplings. I could have kind of picked whatever else, and I've used some thermal-like Lindbladians. Really, it's the thermal operator for one spin, but I use it for kind of tensor producted onto each spin, and you can expand such a thing in a poly basis if you wish. So the details are on the paper. And so what I'm going to show you here is I'm going to start from the left, and I'm going to continue to add O operators that I'm going to throw into this machinery and measure their correlation with all of the polys of a reduced locality. And I'm also assuming that my Lindbladian is local. So I call it J local. So I have K local Hamiltonian, J local Lindbladian. And basically exactly when I've put in enough O operators such that I have an invertible matrix, we see by the singular value decomposition that we have a 0 singular value or a 0 eigenvalue. And that's this thing, and then these points are just the error between the estimated Hamiltonian Lindbladian and the true one. So basically, at this point, it drops off. We also do error analysis and think about a dynamical setting. I don't have enough time to say about them, but I would be happy to tell you more about it anytime. Also in the hardware libraries, Parage has studied the non-equilibrium quench dynamics of long-range spin models. So he considered a system of models which are long-range interacting, so kind of everything can interact with all the spins. And so there's a phase diagram, and what they're considering is, starting off the system in some place along this critical line, and transitioning to a different point. And what they, to summarize, what they show is that there are different, basically, they realize different types of dynamics depending on which part of the critical phase space you were in, which critical point you begin in. So this is a new PRL just come out, and they have thermal dynamics and non-equilibrium dynamics, depending on, again, where you're jumping from. Okay, so Dave should be familiar with this paper. Greg and the APL team are also experts in noise spectroscopy, and they've have some very nice results regarding the use of noise injection techniques and noise spectroscopy to determine and modify noise spectra. So I believe they've kind of shown that they can engineer particular types of noise by putting in correlated noise and also so this gives you the freedom to, I suppose, change the noise properties, and you could do things like, this is kind of where dynamical decoupling and other techniques to reduce noise come in. And this, again, it's actually been done on experiment and works, which is always pretty cool. So send your questions to Dave for that one. And then lastly, here's a paper that's going to come out on the archive. well, I thought it was going to be this week, but I guess it's next week. So we're similar to maybe Indrakshi's result. We're trying to combine the application and the hardware by using some analog dynamics. So in this case, we consider basically this cross resonance effect, which gives you the cross resonant gate, which is used by for example, IBM and others to construct entanglers. And so we use an approximate, we do some kind of low order perturbation theory to determine what the many qubit version of this is. So the picture here, sorry, so I should have said the picture here is like, you have a control qubit, you drive it at the frequency of the target. They're kind of nominally detuned due to the two qubits having different frequencies. But when you turn on this interaction, through the second order effect, you're driving transitions in the two qubit space. Okay, so now if I do the same thing with many qubits, I have the same kind of setup. I drive all qubits to their frequency of their neighbors to the right, and I do my similar analysis to get an effective Hamiltonian. You'll see that you get something that looks like this. So it's a sum of all XZ, and there's also some extra phases that can change the character of this from X to Z. So these are really the same thing, but it's kind of a many qubit version of it. Okay, so then so this is going to be our analog Hamiltonian now, and if we use this guy and we also use some single qubit gates, then we can do some interesting things. So kind of a trivial thing that I can do, but it at least gives me, I can say I have an Ising simulator, is I could just say, drive every other qubit, so 1, 3, 5, blah, 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 in one round, then drive 2, 4, blah, 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 in another round so that the gates are non-overlapping. It's really many copies of this. And then I rotate into the Z basis, and the two operations commute, and I can simulate Ising dynamics in this way. And this is kind of a circuit. And so H is Hadamard. P is P are the propagators generated by these Hamiltonians. And I'm basically toggling between these two Hamiltonians. So I've used my one analog Hamiltonian, and I've toggled it into some other form by single qubit gates. So that's the point. Single qubit gates plus this guy equals some interesting simulators. So going a little bit further with this, what you can do is keep them all on, and then conjugate by act with Hadamard on every other qubit, and that would turn, and some other local rotations, and that would give you a Hamiltonian, for example, that looks like sum over YY over all so YY on kind of, let's say, even bonds, and XX on all odd bonds. So the two terms inside this Hamiltonian do not commute with one another, but that's fine because I'm just going to use it as an analog Hamiltonian. And this is kind of the trick. I'm using this analog Hamiltonian that has some non-commuting character to reduce error from, say, trotterization. So I can construct this Hamiltonian with this toggling that's described in the paper. And then I can construct, the same Hamiltonian translated over one lattice site where I swap XXs and YYs. And of course, if I take their sum, you see that I have the XY model. But now, despite the terms in here not commuting, this O and this E operators do commute with one another. So they're written in terms of their indices here. So, this Y's will commute with these, X's with X's, and so on. And you can come up with a Trotter error-free simulation of XY. And so you can do this as well for 2D, consider a 2D generalization. This is a picture of these two Hamiltonians in 2D where solid is XX's, dashed is YY's, and green refers to the first Hamiltonian, red refers to the second, and this is our unit cell. In this case, they don't commute completely, but you can still basically reduce the bounds for trial error by a factor of 3, and this is a picture of all the terms which don't commute. It's 1/3 of the ones that wouldn't commute in a digital decomposition. And likewise, we can do Heisenberg model using some other toggling between X, Y, and Z versions of our analog operator. Okay, so that's the very quick summary of everything we've done. I strongly encourage you to contact either me or other team members via our website, qcor.ornl.gov. If you wish to get into contact with us, we're very happy to collaborate. So just to conclude, we've done simultaneous work in kind of this scaling invariantly, hopefully on this stack. In the next few years, we want to actually connect the different, so we were just getting started the first 2 years. Now we actually want to connect everything and push the software development and make a working stack. And hopefully the results here are, I don't think that this particular stack will be exactly the one that's used in 20 years in the future in quantum computing, but I think we'll learn lots of things that hopefully have a lasting positive effect on quantum computing in the community. So I'm happy to take questions if there is time. I'm free now, so thank you for your attention.
Right, well, thank you very much, Eugene. Really appreciate it. We'll have time for one question. Are there any? I don't see any in the chat, so if I see one, I'll ask it. But I did have one on the previous work that you just talked about. I guess maybe even the slide before would be a better one to. So this presumably requires you to modify. I guess I'm thinking forward to the implementation, potential implementation on hardware. It requires you to modify the cross-resonance gates as implemented, I think, by watching you talk about this, right? And is this something that could be done, say, on the IBM machine when they're giving you their pulse level access now?
You could try to do it. You could try to do it. Well, what happened is you would get some very disordered version of one of these models. So this theory is kind of is very approximate, and so one thing that you need to do is kind of think about the frequencies of all the qubits and how you might even think about designing a chip so that you could really do this with particular frequencies, and then you'd want to think about there are many deleterious and other kind of there are many other terms that come with these Hamiltonians that one goes to great lengths to reduce in practice, and in calibrating and driving at sweet spots and et cetera, and pulse sequences. So kind of all of those things would be needed to make this thing work really well. However, you can totally try to do it, and you will get some kind of crazy dynamics of some effective spin system, and I don't know what that is, but I'm sure it'll have very interesting dynamics.
All right, thank you. All right, and there's no other questions in the chat, so we'll end here for now as we're right at 4 o'clock. Eugene, thank you very much for. Here's a really quick question you can probably answer.
Yes.
From Jonathan Du Bois from Lawrence Livermore. He wants to know if you're planning to follow up with any of this work with the test beds.
Yes, we have many of the people on the project have their own user proposals on the test beds. We have put in one with Berkeley Lab. I think we'd be happy to, again, the first couple of years we were just developing the basic theoretical protocols in many cases, and there's kind of, as we all know, a whole side for actually implementing them. So I am interested in implementing and using test beds, and I would like to, I would love to talk to anybody who's we enjoy learning from test beds and talking to them and thinking about proposing work. Yes.
Great. All right. Well, thank you again, Eugene, and thank you all for joining. And we'll be back in a month.
All right.
Thank
Thanks
you.
for having me.
Yep. All right. Bye-bye.
Bye-bye.